All right, today we're going to crack the code on something that can look kind of scary at first, quadratic inequalities. But trust me, by the end of this, you'll see they all boil down to one simple, really powerful method. So let's just dive right in.
So why should you even care about this? Well, think about it like this. Imagine you're tracking a rocket launch. You know its flight path, but what you really want to know is, for how long, for how many seconds is that rocket above 1,000 feet? See, that's not a simple equation where you're looking for one answer. It's an inequality, and answering questions just like this is exactly what we're about to learn.
You see, that rocket's path, it's not a straight line, right? It's a curve, it's a parabola. And that means the simple algebra we all learned for lines just isn't going to cut it here. We need a totally new way to think about where that curve is above or below a certain point.
Now, you might be looking at this and thinking, okay, if this were just a regular inequality, I just move the 9 over, take the square root, and I'm done. But not so fast. With that x squared in there, things get way trickier. If you try to do that, you actually lose a ton of crucial information. This is the exact spot where our old methods break down, and it's why we need a brand new strategy. And that new strategy is called the test point method. This right here, this is the key to this entire splainer. It's a super reliable, step-by-step process that turns these problems that look really complex into, believe it or not, a simple little checking game.
The whole thing really just boils down to these 4 steps, okay? First, you find what are called critical points. You just pretend it's a regular equation set to 0 and solve. These points slice up your number line into different regions. Second, you just pick one easy test number from each of those new regions. Third, you plug that test number back into the original inequality and just do a quick sign check. Does it come out positive or negative? Does it work? And finally, you just shade the regions that made the inequality true and write down your answer. That's it. That's the whole method.
Okay, so theory is one thing, but let's actually see how this works in practice. We're going to run through 3 examples, starting simple and then getting a little more advanced, just to make sure we really lock this method down. So let's kick things off with a real classic. X squared minus 9 is less than 0. All we're looking for are the x values that make this whole expression negative.
Step 1, find those critical points. So we pretend it's an equation, x squared minus 9 equals 0. Super easy to solve, right? X equals positive 3 and negative 3. Boom! Those 2 numbers are the boundaries for our regions on the number line.
Okay, now for the fun part, the actual testing. Our points negative 3 and 3 have created 3 different zones. Let's pick a number from the zone on the far left, something like negative 4. We plug it in, negative 4 squared is 16, minus 9 is positive 7. Is 7 less than 0? Nope. So that zone is out. Now for the middle zone. Let's pick the easiest number possible, 0. Plug it in, 0 squared is 0, minus 9 is negative 9. Is negative 9 less than 0? Yes, it is. So that's our solution zone. And just to be sure, let's test the last zone with x equals 4. That gives us a positive 7 again, which doesn't work. And so there's our answer. The only region that actually worked was the one between our 2 roots. So the solution is all the numbers between negative 3 and 3. You know, a good way to visualize this for a less than problem is to think of the parabola as a bridge. We're looking for the part of the bridge that dips below the water, and that's the part between negative 3 and 3. Okay, let's level up just a little bit. Here we've got a slightly more complicated quadratic, and notice that sign, it's greater than or equal to. That little or equal to bit is going to be really important when we write our final answer. All right, step 1, find the roots. We just need to factor this thing. It factors nicely into x minus 5 times x plus 2. We set that equal to 0, and that gives us our 2 critical points, positive 5 and negative 2. Once again, these are our boundary lines. Now here's a fantastic little shortcut. Since we have it in factored form, we don't even have to calculate the exact numbers. We just need to check the signs. So let's test a point on the left, like x equals negative 3. The first factor, negative 3 minus 5, is negative. The second factor, negative 3 plus 2, is also negative. And what's a negative times a negative? It's a positive. We want it greater than 0, so yes, that region works. For the middle, let's try x equals 0. We get a negative times a positive, which is negative. No good. And for x equals 6 on the right, we get a positive times a positive, which is positive. Yes, that one works too. So our solution is actually the 2 outside regions. It's everything from negative infinity all the way up to negative 2, and then everything from 5 all the way up to positive infinity. And notice the square brackets. That's because the original problem had that or equal to part, which means our critical points, negative 2 and 5, are actually included in the solution. All right, last example.
This one looks super simple on the surface, but it's got a really important logical twist to it. We want to find out when x squared plus 25 is less than 0.
Now, before you even jump into the four-step method, just pause for a second and think about this. What happens when you square any real number, positive or negative? Well, it becomes positive, or at worst, 0. So can you take a positive number, or 0, add another positive number to it, and somehow end up with a negative result?
No way, it's impossible. The expression x squared plus 25 is always going to be positive. There is no real number you can possibly plug in for x that's going to make that statement true. So the answer here is simply no solution. See, sometimes the answer comes from a little bit of logic, not just from running through a procedure.
Okay, so now that you have the method down, let's quickly go over the two most common traps that people fall into. Avoiding these will save you a ton of headaches, and probably a lot of points on a test.
First pitfall, and this one is a big one, where you plug in your test number. You absolutely must plug it back into the original inequality, the one with the less than or greater than sign. You're trying to see if that number makes the inequality a true statement. If you plug it into the equals 0 version, it'll just give you a wrong answer every time. And trap number 2 is all about the notation for your final answer. It's actually really simple. Use parentheses, the round ones, for strict less than or greater than. Use the square brackets when you have or equal to, because that tells you the endpoint itself is part of the solution. Oh, and remember, infinity and negative infinity always get parentheses, because you can't actually get there.
So, why did we spend all this time just on this one type of problem? Well, because what you've learned today is actually much, much bigger than just quadratic inequalities.
This is so important, I can't stress it enough. This whole method, this idea of finding critical points and then testing the regions in between, this is a fundamental concept in mathematics. It is the exact same logic you will use later on in calculus to figure out where much more complicated functions are increasing or decreasing. So what you learned today, it's not just a trick for one chapter. It's a foundational skill for your entire math future.
So what's the big idea here? What's the one thing to take away from all this? It's that we can tackle these seemingly complicated inequalities not with some crazy algebra, but by breaking the problem down. You find the boundaries, and then you just test the spaces in between. It's an incredibly powerful way of thinking that turns confusion into total clarity.